All right, we're going to continue with our electrochemistry, and we're going to talk about something called Voltaic cells, okay? In a spontaneous redox reaction where you got reduction and oxidation, electrons are transferred and they move, okay? So when they move, you get energy being released and in the form like a battery, okay? You can see here we have a zinc electrode and we have a copper, and this one's in copper sulfate solution and this one's in a zinc sulfate solution, okay? And they actually, the electrons flow from one to the other. You can see here's this is a voltmeter that measures it, and see how it says 1.10. Okay, if this is a negative 1.10, you'd need to switch your electrodes. You got them in the wrong order. Okay, so but this is going to be the flow of electrons, and again, we can get work done by that. We use it for batteries all the times, okay? So the solutions, you can't see here, it says solution that contact with each other, okay? Sorry about that. I'm covering that up. But anyway, a voltaic cell is a way we can use electrochemistry for a purpose, you know? Okay, so voltaic cell is, again, where you have electrodes and you have a flow of electrons. And it's really what it's doing is it's a redox reaction, okay? So here's a voltaic cell, okay? This is the one from the page before. Here's our zinc, okay? And zinc, if you look here, okay, zinc is going from 0 to +2, so it's being oxidized, right? So we've got those electrons in here. Okay, so this is called the anode, okay? Oxidation occurs at the anode. So if you can figure out where, you know, like we did on before this, where the oxidation is occurring, okay? This is going to be the anode, all right? And it flows, the electrons flow because we've got these electrons being released. They flow over here to the one that's being reduced, okay? And if you look, hydrogen, in this case, goes from plus, you've got your hydrogen ion plus your 2 electrons, and you get hydrogen gas. So it's combined here, and when it's combined, it's +1. And then over here, it's hydrogen gas, it's 0. So again, this is the one that's being reduced, and this is the cathode. So the anode is where oxidation occurs. The cathode is where reduction occurs. And you can remember that electrons always flow from the anode to the cathode. That's, just think alphabetical, A to C, okay? So they move, and this is your flow, and you can have a voltmeter right here to measure how much energy, how much electricity you're actually getting. Okay, so the electrons flow, and sometimes there's some issues with the balance of it. So what they'll do is they put this little gadget in here. It's called a salt bridge. Okay, it's usually a U-shaped tube and it has some sort of solution in it. And what it does is helps keep charges balanced. It's kind of like a buffer. Okay, it keeps things flowing. Without this, you might get an overflow and then it'll shut down. But the salt bridge helps that. Okay, so when you have a voltaic cell, you have some sort of metal that's your anode, and this is where your oxidation is occurring. And then you have another element. This is where your reduction is occurring. It flows from the anode, which is where oxidation is occurring, to the cathode, where reduction is occurring. Okay, so it flows from A to C. And again, the salt bridge here is just kind of a thing to help when you've got a different, if you have charges that aren't balanced, it helps keep them balanced. Like I said, it's kind of like a buffer, okay? When you have a voltaic cell, the electrons are going to leave the anode and they're going to flow to the cathode, okay? One of the things that can happen then is your anode, that metal, can actually disappear, okay? If you've got batteries, you know how they corrode on the bottom? Sometimes that's what happens, okay? So the anode half cell, again, that's where oxidation occurs. The cathode half cell, that's where reduction. And again, you have this. Now, it doesn't have to be a salt bridge. Here they put a barrier that's like a salt bridge. Okay? So as electrons reach the cathode, the cations in the solution are attracted to now the negative cathode. So you get that attraction between them. And again, your electrons are going to flow. Your anode is actually going to be negative because you have electrons. And it's going to flow over to the positive. Okay, and then you get this, again, the salt bridge helps that keep those charges kind of balanced, okay? The cations gain electrons and are deposited as a metal on the cathode. So this one's going to kind of disappear and this one's going to get larger, if you want to say that, okay? when you're looking at potential energy, and again, this is for all kinds of cells, but we have something called the electromotive force, the EMF. And here's an example with a waterfall. We've got, not so much energy here. We got a lot of potential energy, and then we've got a lot of kinetic here. So our high potential energy is at the top. That would be our anode. And then down here at the bottom, that's where you really hit that energy. And that our potential energy is kind of gone because now it's been switched to kinetic. Okay. So comparatively, if you think about it, electrons flow like that. They're going to go spontaneous one way in a redox. They're going to go from high to low, just like a waterfall. Now, a waterfall is based on a gravity, but it's a good analogy to see. It's going to go where there's high potential to low. And again, A to C, alphabetical. Okay. That force, the difference between the anode and the cathode, can actually be measured. And it's called the electromotive force, or EMF. Okay. And you can figure it out. It's also called the cell potential. They have the numbers calculated for most of the metals. So what you'll do is you basically will add them together. And again, I'll show you. But it's measured in volts. And that's that on that first slide I showed you, a voltmeter. 1 volt is a joule per coulomb. Not a big deal. We just deal with the volts, okay? Okay, and here is a standard reduction so you can see the numbers. Okay, if we take iron and we reduce it, this is how much, this is the EMF. So they've been calculated, so you just have to look them up in a chart. And honestly, if I have you do these problems, I'll give you the EMFs, okay? So reduction potentials for many electrodes have already been measured. They've already figured them out, so you just have to look them up, okay? The values are compared using hydrogen as a standard. Excuse me, okay? And again, when you're looking at these, they're standard conditions, it says, well, STP, the concentration is 1 molar, 1 atmosphere, and then 25 degrees Celsius. This is the standards, okay? So when they say standard condition, this is the temperature it's at, this is the pressure it's at, and this is the concentration. Okay, so if we're going to figure it out, if we're going to figure out their cell potential, okay, what we do is we take the EMF for the cathode, and again, these are reduction, minus the E reduction for the anode. So it's going to, now when we're trying to figure it out, it's going to go cathode to anode. It's kind of like the ending, like products to reactants, just like we did for almost everything else. Product to reactant, well, it's kind of the same thing. So we're going to start at the cathode. We're going to have the reduction number, and again, we just have to look it up, minus the anode, and then that'll give us for the cell. Okay, so if we're looking at cell potentials, okay, here the anode, the cell potential is minus 0.76 volts. Okay, we actually flip that and make it positive because we're going to subtract and subtract, negative minus a negative is positive. And for over here at the cathode, the EMF for reduction is plus 3.34. And again, you can just look these up in a table. You don't have to calculate them. So if I'm doing this, what I'm going to do, again, is I'm going to take my cathode, where I end the product, basically, minus where I began. So I take my 0.34, and again, it's subtract, subtract. That's what I was saying. This is going to become positive. And so my voltage for this should be 110 volts. You can measure it with a voltmeter and see how close you are. Okay, so again, that's how it works. You just take the cathode minus the anode. And usually the anode's a negative number, so you're going to make it positive. Okay. Okay, so what can you do with these? Well, we all like to buy these alkali batteries, right? Okay, their difference here between the anode and the cathode is 1.5. So if you have 2 of them, you get 3 volts. And you guys know on your batteries, sometimes you have C, D's, AA's, AAA's. As long as they don't have those flat ones, I'm good. I really don't like when they have those different little flat ones, like for your, because I can never seem to find the right one of those. Anyway, the biggest thing we use electrochemistry for probably is for a battery. And it's a portable, self-contained electrochemical power source, okay? And really what it does is that each one of these are a Voltaic cell. Okay, the batteries can be primary cells, which means they can't be recharged. When they're dead, which most batteries is what we use. The reaction is complete, it's over, or sometimes they have secondary cells which can be recharged. I've bought rechargeable batteries and it doesn't, after the first time you recharge them, they don't do very well, I don't think. So most of the time we buy batteries that can't be recharged. Okay, and the other thing that we can use for these cells is to prevent corrosion. We can use rust proofing. Okay, because when you do have this reaction, you're going to get, one's going to wear down and one's going to add to. So we can prevent it by doing some things with our cells. Okay, another thing you can do with application of Voltaic cells is electrolysis. One of the most common way electrolysis is to take water and break it down into hydrogen and oxygen gas. Okay, again, you're using electric current to break it down into its two components. So there's all kinds of things we can do with Voltaic cells. My guess is this is the one you're most common with, is the batteries. Okay, and there's different kinds of batteries. We have lead acid batteries where the reactant products are solid. So the potential is independent of that, but we have to put something that works as a conductor, and it's usually sulfuric acid. If you've ever spilled battery acid, now the batteries are a lot better, they're contained better, but sometimes they used to leak and it will destroy your clothes. Okay, we have alkali battery, which is the most common primary battery, which we buy now, our little battery cells. Those are the most common. There's nickel cadmium batteries, where nickel is a hydride. It's lightweight, it's very rechargeable. Cadmium is toxic and heavy, so hydrates are replacing it. A lot of our cell phones and stuff have these type of batteries in them. We have lithium-ion batteries, which are nice because they're very, very light, and they do produce more voltage. They cost more, I know I have a Vexlar that I fished with, and I had a nickel cadmium battery, and now I've replaced it with a lithium battery, and it goes forever. I seldom have to plug it in and recharge it. Okay, so here's some of the batteries, the pictures of them. We have a lead acid battery. This is like a car battery. You have you have quite a few grids, it's not just one cathode and one anode. Here you have several, because you're going to need more, power to get that car started and stuff. That's the most common thing to use this for, is the lead acid battery is for your car. Okay, the grid is filled with a spongy lead, which is your anode, and then the lead grid is your cathode. And again, remember, anode to cathode, that's where it travels. And again, your electrolyte, your liquid in here to help make sure things move along, is sulfuric acid. Here's an alkali battery. It's a little different. See how your anode's on the bottom and your cathode's on the top, and you have a separator. That would be like a salt bridge. Okay, so it's right in the battery there that you have your anode and your cathode. And then we have a lithium-ion battery. Like I said, these are relatively new, but these are, I would say, most people look for these because they seem to last the longest, and you can recharge them, and they're wonderful. Yeah, I like I said, if you can get a lithium-ion battery, you don't have to charge it so much. It has, it lasts a lot longer. And you can see that even in the batteries. You can buy alkali batteries, but if you have something that you're worried about, you can buy a lithium battery. They cost more, but they last a lot longer. So here in a lithium-ion battery, you have your anode, which is your and again, remember, it goes from anode to cathode. Okay, and it depends. You can see, I'm trying to read on here, the graphite anode. Graphite would be carbon, so you have layers of carbon, and then the cathode is usually something like cobalt or lithium. Obviously, you need some lithium in there, so you have more than one metal in these cases. Okay, and again, you get the ions formed. You have oxidation here, you have reduction here, you get that flow of electrons, and this is what we use up here. This is why we have batteries, for that flow of electrons. It gives us, and again, that's the biggest thing I use electrochemistry for. And I want to say I'm done. Yeah. Okay. So we're done with that part of this chapter. We got one more section to do.